Okay, so in this example we have a thin homogeneous bar P of mass little m and length d, which is constrained to move within a smooth slot cut in a frame, and we're told that the frame has negligible mass. The frame is pinned to ground at end O, and initially the frame is rotating with the speed of omega 1, and bar P is stationary with respect to the frame and centered within the slot. We're told that the center of mass of P is along line OA. We're then told the system moves in the horizontal plane, and that basically the center of mass of P moves a distance d outward in the slot. We're asked to find the new speed of the frame. Okay, so how are we going to go about doing this? Well, we can note that the frame has negligible mass here, and so I can draw a free body diagram though still of the system, noting that because we're trying to find an angular speed after a change in position, that we're going to need to use some method here, and in this case I'm going to choose to use angular momentum and see if that gives me a good result. So if I draw a free body diagram for the system, here's my system, I can note that I have forces here at the reaction point O of OX and OY. And since I'm in the horizontal plane, that's actually it. So the nice thing here to note is that because there is no moments about point O, I have that H about O at state 1 has to equal H about O at state 2. And because this is true, what I can say is that I about O times the initial speed omega 1 in the k direction has to equal, and I should call that I about O at 1, I about O at second state 2 times omega 2 in the k direction as well. So dropping the k's, I can say that omega 2 is equal to I about O at state 1 divided by I about O at state 2 all times omega 1. So really this problem comes down to finding I about O at state 1 and I about O at state 2, and this is a relatively straightforward thing to do because what we have here is essentially a thin bar which is moving positions. So in this case what I can do is I can find each of these quantities. So I about O at state 1 is going to equal I about its center of mass at state 1 plus the mass of the bar times the distance from this point here, which we're going to call point A, to point O quantity squared. So if I do this, I for a thin bar is 1/12 the mass of the object times its length squared. I'm going to add to that m times r squared. At the second state, we're going to move some distance either up or down, and this is going to mean the distance between this new point, which I'll call B, and point O is now going to be a hypotenuse of a triangle. And so that means that I about O at state 2 is going to equal I about G at state 2 plus m times the distance between B and O at state 2. Again, the I about its own center of mass won't change, so this is going to remain 1/12 md squared. But my new distance, it'll be the hypotenuse squared, which will be in this case r squared plus, if we're moving a distance d, the center of mass is simply going to move up a distance d, so we'll have plus d squared. So we can take these two values, we can plug them right back in here, and we can solve for omega 2. And of course we know that omega 2, the velocity vector, will simply equal omega 2 in the k direction. Okay, I think that just about wraps us up for this problem. So I'm going to bid you adieu and the best of luck. Take care, everyone.